Okay, let's get started. So last time we stopped at this point. We're talking about the serial engine. So the engine that controls all the events in the simulation and how it advances times, right? So I will skip this part. I will directly go to the last part. That is the essential part of the serial simulation code. So in a serial simulation engine, we want to execute one event after another. Even if they're scheduled at the same time, they will be executed in certain order. Okay, so how is the event order is actually determined if they're scheduled at the same time? Quick answer is we do not really decide them. We consider they should be independent and it shouldn't really matter that which one executes first or execute later. The order is actually determined by goals heap implementation. So the heap, when you pop, if they have same time event, then it really depends on what's the internal implementation of the heap to give you the next event to execute. Okay, it can always guarantee that is the earliest time to execute, but it cannot guarantee which one it returns. It cannot guarantee the original order as scheduling. So last time we were talking about serial simulation. Then let's start with parallel simulation today. So when we talk about synchronous sequential logic, we know it's a group of registers and combinational logic. And this combinational logic and that combinational logic, these two logics, they're executing in parallel because they're executing within the same tick, right? Then both of them take their input, right? Their input, and they can generate output either if there's a loop or if there's no loop, right? They always, for a certain type of input, they generate output, and they will get the input from this cycle. They will generate some output. They can never actually get the output of this CL. So the second CL will never get the output of this combinational logic within the same cycle. It must be the next cycle, right? So that is to say, any behavior, any logic in digital circuit, for every cycle we have a fixed input. Then when we do calculation, we generate a fixed output. The output may becomes the state or may control the state of the next cycle. In this way, if we have many combinational logics in your simulation, we actually can simulate all these things in parallel, right? So that means if events that are scheduled at the same time can be executed in parallel. In this way, we can support parallel simulation. Let's see how we support parallel simulation in Akita. So remember, we have an engine, right? Each engine has these five functions implemented. So we want our parallel engine to follow the same interface. So it will follow the same interface. It only still have these 5 methods. Now, from the perspective of a component, when they are scheduling events for the future, or when a user is implementing a component, the component is the most part that the user may want to implement the digital circuit logic, right? So in this case, they don't really need to know if they're working with a parallel engine or working with a serial engine. They only they're knowing, oh, we're working with an engine, and I can schedule an event, and that event will happen in the future. So it really, I would say, this is a programmer transparent way of implementing a parallel simulation. Then how does the parallel simulation works? Then the code is actually a little bit long. Then it's much longer than serial simulation. So let's look at this code together. Then then you will understand how it works. Okay. So at the beginning, it's basically the same. When there's no more event, we just exit, right? Then here we set a lock. This is a pause lock, just the same thing as serial simulation. Then here we have 2 functions. One is determine what to run. One is run round. So what is a round? A round is basically the event that are scheduled at the same time. Okay. Run round, that means we run all this, we handle all these events if they're scheduled at the same time in one cycle. Now here we run rounds, right? We run multiple rounds here. Yes. So here I want to say, I don't know if you noticed that in Akita we typically hate comments. So for all the code that I showed you, those are real code. Those are the whole full codes that I'm showing you. It's not something I remove the comments and showing you there. We hate comments. We think comments. So these are not comments. These are not comments. These are code documentation. Okay. So for Go, if you know Go, the go.pkj.dev, it's a website, and then you can check the automatically generated documents. So those are documents that you can view in a web page. Those are documents. Those are not comments. So within a function, we rarely write comments. Then, so for people who pro writing comments, they think if you have comments, the code is easier to read. Then, like typically, I have the opposite feeling, that I find that when you write comments, the code becomes harder to read, especially in real world. When you are dealing with this scale of code, it's okay. But when you're solving a complex problem, if you don't care about coding quality, it can easily grow to hundreds, thousands of lines long. Then you write comments there. Then someone else will come and start to modify your code, but forget to modify the comments. Then the comments has mismatched with the code. Then the comments is misleading, right? So rather, we care about the readability rather than how many lines of comments that we write in our code, right? So how we can guarantee readability is we try to use function names instead of code. Okay, we think determine what to run and run round is more. These function names you can just consider their comments, right? But they're very, very likely to be describing what is actually happening with this function. So we break down this long function into smaller functions, and for each group of functionality, we use smaller functions to fix this, to achieve this goal. Okay, there are lots of debate on comments. Then my general consideration is, unless there's something that's really tricky, then we should avoid comments as much as possible. Okay, so let's read the code a little bit by a little bit. So we are breaking down into the determine what to run. Now here, the determine what to run is basically just to find the time that we need to run, the time. So basically in each queue group, I'll talk about queue group later, but you can consider there's a list of queues for primary event and a list of queues for secondary event. So we find the earliest time in primary queue and the list of the earliest time in the secondary queue, and we set the primary queue and the secondary queue. So if the primary queue time is earlier, then we consider we're running primary events. Otherwise, we're running secondary events. But here we only just say, oh, this is the time of the next round that we need to execute. Okay. Then here comes the run round function. So run round function, we get queues. Ignore queue channel for now. Then if we're running secondary events, we're doing this. Then we first empty the queue channel. Then we run events until we cannot run more, until conflict. We try to run as many events as possible. Okay. Then, so let me slightly explain what queue-chan here is doing. So in serial simulation, we only have two queues, primary queue and the secondary queue, or you can consider there's only one queue for simplicity. Now we find in parallel simulation, we want to execute these events together at the same time, right? Then we are actually pumping out events from this queue and dispatching them to the runner, and runners are executing. While we're pumping out events from this queue, we kind of are locking this queue, right? So when we're locking this queue, but the events, when we're handling events, they want to schedule new events into this queue. So this queue becomes a global performance bottleneck that everyone is waiting for this queue. So it has to first dispatch everything so that it can handle new scheduled event. On the other side, these new events, when they're want to insert into this queue, they have to be serialized. So they have to insert one event, insert another event. So we realize that becomes a global bottleneck. That's why we convert a single queue into multiple queues, so that even we're pumping out events from one queue, we may be able to schedule into other queues, so that these two things can happen at the same time. So it's a performance optimization. What is a queue chain? It's a channel. It's a Go's parallel simulation feature. You can consider it's a pool of queues. Now, whenever we want to pop up a queue, we actually can retrieve a queue from the channel. It's just to get a queue from the pool. Okay, so we first empty the queue chain so that this pool, we want to take all the queues out of this pool so that no events can schedule in it. We have to make sure that this queue, we dispatched all the events from this queue that are scheduled at this time, then we put it back into the queue, into the pool, so that other events can schedule event into this queue. Okay, this can be a little bit complex, but not something super essential. Then we run events until conflict. Then I think this code start to get something that you're rather familiar with. It's very similar to serial simulation. So here we have this queue, right? We range through the queues. If there are events, we get something from the queue. If the event time equals null, if it's within this round, right? Then we do queue.pop, we remove from this queue, then we run this event with a temporary worker. Okay, we run it with a worker. Now otherwise there's something wrong, then eventually we put this queue into the pool, right? This is a syntax of putting this queue into the pool. So the only special thing is run event with temp worker. Let's look at run events with temp worker. It's this thing. Run event with temp worker, we call go e.temp worker run. This is a very simple syntax. That means we're starting a new thread to run this event. So pretty much here we're using one thread to run one event. Go threads are much lighter weight. So although we have billions of threads, it's not a big problem. We can handle them. So here there's a wait group at 1, right? This is a synchronization. So remember here we have, just go back a little bit, we have this wait group .wait. So we have to wait until all these events within this round to finish, then we can start the next round, right? So this wait is a synchronization. And that's what I say is a big performance overhead for Akita. So we're doing something that is called a conservative parallel discrete event simulation. A conservative discrete event simulation means we do not interrupt the time. We guarantee the time still goes in the right order. Then so that ideally the execution result or the predicted time in parallel using parallel simulation should be exactly the same as serial simulation. Okay, so we do not interrupt the time order. The chronological order is maintained. The good thing is the accuracy is somehow guaranteed. The bad thing is it cannot reach very good scalability. Okay, so there's still space for research to make it more, the performance to be higher. Okay, so we add one event, then we're waiting for this event, this wait group, this number, this task to be done. So here, this run event with temp worker or temp worker run is actually very simple. It's basically the same code as serial engine, right? So we get the time, we do some sanity check, we call a hook. Now here, this is when the events are actually happening. Then we call the hook after the event again. Then wait group is done. When it's done, that means we're reducing that wait group counter, add 1. We're reducing this counter down by 1. When it becomes 0, we consider weight group.weight is completed. It can pass that point. Okay. So this is the parallel engine. Then, so the key idea is only one sentence. If events that are scheduled at the same time can be executed in parallel in Akita. Okay. Then, so how many of you know solid design principles? Solid design principle? Really, no one? Solid design principle is a software engineering concept. Okay, no one, right? Then it's very important. Then I hope everyone can learn it. If you write some non-trivial scale program, some slightly larger scale program, solid design principle is very important. It's very, very useful. It's actually 5 principles. And I'm trying to just go through these 5 principles and see their examples in how we use these examples in the simulator. So how many of you know design patterns? Okay, only a few of you. I think the undergraduate 304, the software development course, teach design patterns, right? And probably also solid design patterns. So these are 5 principles. S is single responsibility principle, always open close. Then this is probably the most important principle. L is Liskov substitution. I think this is probably the least important one. It's not that relevant for Go. I is for interface segregation. D is for dependency inversion. So I will go through every principle with you while we're introducing the simulator. Dependency inversion principle describes this behavior. So for if you want to make the program really simple, you say, oh, I have a handler, right? Handler, let's say internally we may need an engine. Actually, the requirement of need an engine violates I principle, but let's not talk about I principle here. So here we have an engine, right? It's a field. It's a field of 0. It's a field that belongs to the handler. When I schedule an event, I can schedule to this engine, right? So I need a reference so that I can schedule future event. Then if you do not consider the structure of the program, you may just say, oh, I wrote a 0 engine and I'm happy with that. I'm just directly say, oh, this engine should depend on this 0 engine. So this engine, I may write a code like this, var engine 0 engine. Or I may put a star here. I may write some code like this, right? So what's the problem with this code? For smaller scale program, it's not a big problem. But it's a hard dependency. That means, or handler, this particular handler, have a hard dependency on a 0 engine. One day, if I want to replace 0 engine with something else, with a parallel engine, I have no way to replace it other than modifying the code here to parallel engine. Now, if you think you may have hundreds of different components in a simulation, then replacing them is not a realistic task, right? So this is a hard dependency. The goal of dependency inversion is to eliminate all hard dependencies. What you should depend on, you should not depend on anything that is concrete, but you should depend on an interface, right? So I depend on engine. This is an interface. Then this is a arrow. This arrow is an implement, right? The implement. So 0 engine and parallel engine both implements the engine interface. That means if I write here as not 0 engine, but the engine, then my engine field is flexible, that I can change to whatever engine that I want. Right? I can even write a new engine here. Right? That's another engine. So this is dependency inversion principle. Then this is, you can consider this is a dependency, but implementation is also a type of dependency. Why? You can see these arrows are not like in random direction. It's always pointing from this subfield to this interface. Why is it? Because you can consider this arrow as aware of. So the handler, because it has an engine, in this case, the handler is aware of the existence of a zero engine. Aware of, right? In this case, the engine aware of the handler is aware of the existence of the engine interface, but it doesn't know the existence of a zero engine or a parallel engine. It doesn't know. It's not aware of, right? Then the zero engine and parallel engine, because they're implementing an engine. Let's consider Java for a little bit, right? When you write a Java code, if you want to implement the interface, you need to write class zero engine implements engine, right? You have to write that of code. If you do that, you are aware of the existence of an engine. For Go, it's a little bit different story. You can be not aware of the engine. That's another type of story, but let's just come back to the old school object-oriented programming way. So in this case, parallel engine and serial engine knows the existence of engine. So what is dependency inversion? Dependency inversion is, previously we have this dependency downstream, right? This aware of downstream. But here we have this dependency at this point going upstream, right? Where inversed this arrow, rather than directly depend on this thing, we're inversed to go upstream. So that's why it's called dependency inversion principle. In this case, we can remove any hard dependency. So basically, when you write a handler, when you write a piece of code, a class or something, a struct or something, when you have a field, you know, oh, this is my dependency. I depend on an engine. At this point, if it's a concrete type, it's a validation of dependency inversion principle, then you should consider creating an interface in between to make it dependency inversion and to prevent hard dependency and to guarantee that you always have the possibility to replace something. Okay, so you can later on you can see throughout the development of Akita, we try to use dependency inversion principle as much as possible. I'm pretty much sure Akita part, MGP sim may slightly violate that, but Akita part should be no problem. Always following this rule. Okay? Any question? No question, okay. So that we're done with the time management part, the engine part. So we're now moving to Akita components, which is another important part. So what is Akita components? It's a basic element of Akita-based simulation. So what is component? Then you can consider each combinational logic and its associated register as a component. But since we're going towards architecture level, we do not really think at the individual register and combinational logic level. We consider components as a larger element, like a CPU core, a GPU core, a cache, memory controller, network controller. Those things are components. Still, there's no certain rules for you to say at what granularity you are creating a component. It's totally okay that you create a component that is a gate. Okay, it's totally okay. You can also create a component, say, in a CPU. Later on, we'll talk about like pipelines. Now you can consider each stage of pipeline as a component itself. You can also consider whole core as a component. So either way works. There's no certain requirement to say what's the granularity for components. So what is we typically draw a component in this way, right? Just a block. I know in some other simulators, components can be called different things. For example, Gen 5 calls a component a sim object. Then some other simulator even just call it a box or block. They're pretty much the same thing. Nothing really new here. So what is a component in code? Then it's an interface. Then are you familiar with this syntax? Or at least you can guess what's going on here. So these are called embedding, right? Embedding is basically a little bit like inheritance in Java. So named is an interface by itself, right? Named is an interface by itself. The handler is an interface by itself. We already talked about handler interface. Handler has one method that is handle. Handle what? Handle an event, right? Handler. Now we'll talk about hookable port owner later. And other than these four, by the way, named only have one method called name. So basically we say this is something has a name, right? Then other than this, we have a notify receive and notify port free. Later on, you can see these two functions are super useful. Okay, so components is a large interface. It can contain many different things there. Then why we want to have these smaller interfaces? Because we want to support this interface segregation principle. That is the I principle. Okay. D is dependency inversion. I is interface segregation. What is interface segregation? In the field of software engineering domain, interface segregation principle, or ISP, states that no code should be forced to depend on method it doesn't use. Do I have an example? No, I don't have an example. I think I have this one is actually a good example. So a handler, right? This is in the environment of a handler. Or you can just consider it as a component, right? Component needs to have engine. Component needs engine to schedule event, right? So eventually this one will say H is this handler dot engine dot schedule, right? So remember, you can go back a lot of slides. Do you remember what's the engine interface? Engine has at least five functions, right? So does the handler require run, pause, and continue functions? Does it require that? Those functions? It doesn't. We only need to schedule future event. We don't need to control the run. We don't need to trigger the run in a component. We trigger a run in the main function. Right? We trigger a run in main function. So this is what I say a violation of the I principle, interface segregation principle. Why? Because we're forcing this handler to depend on the run and pause function, although it doesn't really require to depend on those functions. So what is the best way to solve this problem? The best way to solve this problem is rather than providing an engine interface, we provide another interface called event scheduler. An event scheduler. Then we let engine to use this method. Say engine should be an event scheduler. If it's an engine, it should be an event scheduler. In this case, if it's a component, it should be a named, right? In this case, an engine should be an event scheduler. So here, rather than an engine, we should depend on an event scheduler. Okay, so this, if I make this change, I'm following the I principle. I only depend on event scheduling features. Okay, that is something that we're trying to improve in Akita v4. Then I think we're almost there, but I cannot guarantee that we have to solve this problem everywhere. So there are still lots of components that are depending on engine, but I think this is a not super important problem as compared to the dependency inversion principle. Dependency inversion principle really makes your software super flexible. Okay, so come back to simulation, complex architecture simulation. Now, this is not software engineering course. So for a component, we have ports. So if a component needs to communicate with another component, it needs to go through ports. And ports support component communication. Now, if we send things out, we call it, or the unit they communicate, we call them messages. Or in other like in other computer architecture simulator, or if you write a paper, the community kind of more prefer to be packets or packages. I'm always confused with these two. It's packets, right? So this domain typically prefer packets. So when you say when network packet, you send a packet out, then it receive a packet. So this is a network terminology. But here we just call they are messages. We send them messages. So if you come from the Akita V1 or V2 time, if by that time if you were using Akita, we call messages request. Then we think request is a very common term, right? Very easy to use. Then we create a problem. We send a request. Then what's the thing that responds to us? It's a response, right? So it creates a huge dilemma or problem for us that we're saying a response is a request. Because we're sending requests, right? Something comes back is a response, but what we're sending is still a request. So a request is a response is a request. It makes these terms really confusing. So we change it to messages. So a request is a message, a response is a message. That makes it much more comfortable. So what is a message? Message is a piece of information that is transferred between components and it has two interfaces, two functions. The more important one is meta. It returns the metadata associated with this message, right? So what is in the metadata? It contains an ID, identifier, a source destination, a traffic class, a traffic bytes, okay? So here, let's say ID. Why we need an ID? We need to record that which message is sent. It needs to be unique. That's why we have this clone method. So we guarantee, let's say, sometimes we have a component A sent to B. Then B is only something like a router. So B is or just pass message to the dispatcher, the pass message to the next point. So it actually can reuse this message to send to the next level. But because of the ID, we have to guarantee the ID to be unique. So we require that message are all disposal. They're all single time use. So use once, you discard it. If you really need the same message again, clone it and use the cloned version of message. So a cloned message, most of the time, is basically the same thing, but only the ID is different. Okay, so message meta return this thing, source and destination. We want to know where we send it out and where we're sending it. So this is a relatively new change. This change is less than 2 months old, that we're starting to use remote port. I think like there are several of you are using Akita, probably still not really aware of this change. Previously, we have a reference, just port. And remote port here is a type alias or another type that is basically a string. So it just requires we don't need to have a reference to source port and destination port on their own, but we just need the name of them. That's good enough for the routing purposes. right? Why we make this change? Yeah, there's several reasons. One reason is in the future we want to support serialization, so we want to prevent circular serialization dependency. Not that important. You just want you know there's a source and destination attached to each message. There's a traffic class and traffic bytes. Traffic bytes is easy to understand. If you say, oh, this message is 1,000 byte or 4 byte, like how many bytes? It depends on how long time you need to pass this message. Traffic class is more related to virtual channel than when we will talk about it when we introduce network on chip design. So traffic class is basically not really being used. It's more like a future-proof field. Okay, so let's look at port. What port can do? Now, port is a much more complex component. It's named, it's hookable. Now we'll talk about hook later. As remote, convert the port into a remote port. Basically, return a name. It's exact same function method as the name method. Okay. Then there are setter and getters. Set connection. What's the connection that is attached to a port? So connections are outside the component and are connecting two ports together. Okay. Set connection and component. What is component? That is the owning component of this port. Okay. There are a set of methods. For example, deliver. So you can see I write a comment here. These a few functions are for the connections to call. So connection will deliver a message, put the message into this port, notify available, tell this port or the connection becomes available, retrieve outgoing. So when we're sending out, it retrieve a message from the buffer, or peek outgoing. So peek and retrieve are two commonly used terms in Akita. The peek means peek and retrieve, they all applies to buffers, right? Peek means we get a reference to the first element in the buffer without destroying it, without removing it. Retrieve means we return that one and also destroys it. Okay, both of them return messages. And same thing here, it's basically symmetrical to connection, right? So we'll have more explanation later. I will go through you with some of key functions implementation to let you know why ports are actually a super important element in Akita. So ports, within every port, there are two buffers. One is incoming buffer, one is outgoing buffer. And also these changes are not very old change. Then in V3 time, each port only maintain the incoming buffer and the channel maintains the outgoing buffer, which we find is very confusing. Nobody can remember this. Then we just make it simple. Just say port maintains both buffers. Okay, so then there's a connection. The outgoing buffer sends messages to the connection and incoming buffer sends the messages to components. Okay, should be straightforward enough. And actually, the connection should retrieve outgoing. Then the component should retrieve incoming. Right, just retrieve elements from these buffers. Okay, so what is a connection? The connection is it's actually much simpler. So I only want you to look at plugin method. In plugin method, we just associate a connection with a port. Okay, then the port also has a connection. Then when we call plugin, we also set the port to work with this connection. So one connection can be connected to as many ports as possible, but one port can only connect to one connection. Okay, so again, a connection can connect many ports, and because we have the source and destination, it can send from any source and destination as long as they're connected to this connection, right? Then, but a port must work with only one connection. It cannot also go with another connection. Okay, and we actually have the sanity check so that if this port is already connecting to something, then if we try to replace the connection by connecting to something else, then it will panic. There's an error. And also this unplug method, we also leave it there for future proof, although we never implemented it. For a computer architecture, it's very unlikely that you change configuration while your program is running. So unplug is a never implemented feature. So I want you to look at a default port. And actually, there's only one port implementation. So if you want to have the port have another feature, copy paste this code, implement your own port. Okay, then using this dependency inversion principle, you can always replace a port of a component. And because your port is still following the same interface, you may have new functions. You can always use your new port for your component. Okay, so this is default port. Nothing really special. It has a name. It has a component. It has a connection. It's all single elements. It's not an array. Then it has an incoming buffer and outgoing buffer. There's a log that prevent some race conditions. So when we create a new port, we need to specify what is the owning component and what's the incoming buffer cap and outgoing buffer cap, the capacity, right? How large are they? Then basically we knew a port, we set a component, we do an incoming buffer, we create a new outgoing buffer, and we set a name. By the way, in Go, if you're not that familiar with Go, Go doesn't really have constructor. So they just use this simple new function to construct some element. Okay, and also in in Akita, there's a naming convention. Now we name something as this. We name something as GPU 0. It's all example, right? We don't really have to be GPUs. The GPU 0 SA1.cu 0 incoming buffer. Okay, this is always the naming convention for Akita. They're separated by dot. If it's a group of or list of elements that are symmetrical element, we use this square bracket. That basically means whenever we have a square bracket here, 0 and 1 have the same configuration. Okay. So those are naming conventions. These are new function. Then there's no real logic here. So I want you to check this code, this send code together. So something I'm pretty proud of the Akita coding quality is pretty much every function I can put on a slide. There's no super long functions. And this is the whole function, right? This is really the whole function. Okay, so we first lock it, then see whenever before we exit the program, we unlock it. Here we do message must be valid. So if you do not care about coding quality, you may just put all the sanity check there. But we know this is probably less relevant to the real logic. We put it in a separate function. And the message must be valid. Whenever you see must, that means if it's not valid, it will panic. Okay, that's a convention. Message must be valid. We check some sanity checks. For example, source and destination must be given. They cannot be empty. And source and destination, the destination cannot be this port. You cannot send back to yourself, right? Basically, there's some sanity check in this function. Now, it's not super important, but here we see if we cannot push, we cannot put it in the outgoing buffer. What we do is we return a new send arrow. We see there's an arrow, we cannot send it because I don't have buffer, right? Then the main component will wait and retry in the next cycle. We'll do something else anyway. Or it's not important, it may just discard it. It really depends on the component logic. Then here, let's look at this one. Outgoing buffer.push. and we push the message in the outgoing buffer, then eventually the connection will take it away and will deliver it to the destination. Just we don't know how long it will take. This part is hook, not super important. And here, this is a little bit important is if it's empty, right? If it was empty, then, and there's a new message arrives, we need to tell the component, it's notify.send. We need to notify the component, there's a port wants to send something. Then the connection needs to wake up and start to work on things and deliver things to the destination. Okay, we need to notify the connection. In a cycle-based simulation, if you consider a connection is a component, we may just simply tick connections, tick, 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 at every cycle, the connection, right? Here, definitely there's a performance improvement trick. If this connection is idle, just don't wake it up. Now, if there's nothing to send on this connection, don't wake it up. Just don't even schedule an event on it. Don't take this connection. Only when we need it to do something, we notify it. Okay, it's notify send. Okay, deliver is the other way around. Now we see how we can eventually deliver something into a port. You can see there's definitely some symmetric implementation, right? So log, check the incoming buffer if we can push. If we cannot push, we say a send error. We say, oh, we cannot deliver at this moment. Try again later. Then was empty. I think. Yeah, this one is outgoing buffer, right? So for sending out is outgoing buffer. For deliver is incoming buffer. Pretty much is only the incoming buffer and outgoing buffer is different, right? Then invoke hook incoming buffer.push. Then eventually we notify this component. Oh, there's a new message. Wake up and process it. Right? So the port here is a kind of intermediate between a component and a connection, and waken them up whenever there's a request that needs to be responded. Okay, let's look at incoming, retrieve incoming. Then who is calling retrieve incoming? It's basically the retrieve incoming. The component is calling retrieve incoming, right? I also need to think for 1 second. So who is calling which one? Then retrieve outgoing is basically exact same code. So probably I won't just show it. So here we try to pop it from the message, from the buffer. And when we pop it, it's empty, right? If it's nil, it's empty. We return nil, right? So it's still we process special cases at the beginning and return early so that we can reduce one level of indentation. Then this item must be a message, and we call hook. Then, so if this incoming buffer.size equals capacity -1, that means it was full, right? It was full. Right now it's not full. We have at least one space available. In this case, we need to notify the connection, say, so the connection may think I'm fully occupied. Like if I'm fully occupied, just don't try to retry sending it to this component, right? But this time I'm not full. So if the connection has something to send to me, the connection can wake up and then notify the connection, say, this port becomes available. Just try again if you have something to send to me. Okay, so that's why I need a notify available. So similarly, on the other side, we have a notify available for the component. Okay, that's the implementation of the ports. Now for connection, I'm now going to show you the implementation of a connection. Connection has longer code, but not very complex. So we have a direct connection. Direct connection, you just can consider it as a wire, a piece of wire. You can always send something from one place to another place without latency. Or if you consider a buffer, it's 1 cycle latency, right? So I will assume that you can imagine how the component connection works. So let's see an example, a ping simulation, create a pure event-driven simulation in Akita. Okay, we want to simulate a ping example. So ping is a network protocol, right? You try to see if nothing is alive or not. You send a ping message and wait for a response. So we just want to simulate this process. So A send a ping request to B, and intentionally we let B to wait a little bit, and it will send a ping response back to A. So here we want to make it simple. So we said these are direct connections, they're latency free. So we have to add a little bit latency, so we add a latency to B. Okay. In theory, if you are doing a network simulation, then you should have a latency on the connection. So let's just go through what type of event we need to have and what messages that we're sending. Walk through this example is we need an event to say at this time we need to start a ping to send this ping out. So we have a start ping event. When this start ping event is called, they send it to this port. Then after some time, this connection will guarantee this request to arrive at this point. So this is a receive. So receive is not really a event. So that's why I'm drawing at a circle. When we receive it, the B's notify receive function should be called, right? So B should be notified that this message is received. In this case, since there's a delay and we know this delay, say 2 seconds later we need to respond, then we schedule an event 2 seconds later. So there's an event, and these two events are definitely should have different behavior. And since we want to keep A and B are the same, we have to have another event. Okay, now when this event is handled, then we send it back, we send the ping response back, and then it receives the ping response. Then we know what's the latency of this round trip. Right? So 2 events and 2 messages. And that's basically what we need. So how to implement it is to create a message. Where's create event? Okay, create events is later. Let's create messages first. We create message, we create a ping message. We only need a message meta, right? Then we can associate any data we want with a message. Now here we only attach a sequence ID so that we know which one comes first. The return may be in different order. The ping message, the meta is simple. This is a boilerplate code. We need this to return this message meta. Clone is also boilerplate code, right? Then generate the response. We need a one method called generate response. It always generates this ping response and have this information. And what is a ping response? It's similar to it, very similar, but we have a response to as a string. Okay, and it also has sequence ID. Meta and clone are pretty much the same, but here we need a get response to message that to say it's a string, which should be the ID of the request. Okay, so that we know which request I'm responding to. Okay, this response to field is the ID of the original request. So we can match the request with the response when we receive it. So we say we actually have other interfaces. We still have the request interface and response interface. Request interface is the message plus a generate response. And the response message is a message plus get response to. So we know which is a request and which is a response. Then we create messages, we can create events. 2 events, one start ping event. We also associate the destination information, say where we want to send it as part of the event. Then for this event, respond ping event, we attach which message we're responding as part of the event, so that when we handling this event, we know the context, right? So if you may not know what's event based. Event based is basically a struct. So this is embedding. It's a little bit similar to inheritance in Java. So if we're embedding this event base, we automatically have the method. Other than this new, we have time, handler, is secondary, these things. So we're basically just trying to avoid you writing too much boilerplate code so that you have these getters ready. Okay? Any questions? Okay, since we have a event and messages, let's try to make it work and try to create a component. So in Akita, we just simply call every component comp. Then all components should be named comp, but the package or the folder name should tell, oh, this is what component this is, right? And also we do require the one package, one component. Don't try to create multiple components within one folder. Component base is also similar to event base. It's just provide you the boilerplate code. We have one port that's called output, okay? Then we have an engine. So see here, this is a violation of ISP principle, interface segregation principle, right? Not a big problem. We'll work on it, probably in V5. So start time, we're recording the event time and next sequence ID. Some internal state. You can consider these states are registers for a component that needs to remember. So let's go through this process. So remember, a component is a handler, right? So the handle is probably the most important function within a component. So we're handling events, although we don't know what type of events we're handling at this moment. So in this diagram, we're doing the start ping and this response ping, not pinned. These 2 points, right? Or solving this 2 points. We have a lock just to prevent this event being handled at in two different events at the same time. For most of the time, you don't really need this lock because later on we're going to implement ticking components. You don't even need to implement handle. You only need to implement the tick function. But that's something we're going to talk in the next lecture. So, are you familiar with this syntax? This is one of my favorite syntax in Go. So this is called type switching. Here, this is an event, right? We don't know what type it is, but we're switching according to the type. And other than doing this switching, we're actually defining another variable that has the same time E. And this internal E within this switch, this new E, has the type of start ping event or end ping event. Okay, so it's a type conversion plus a type switching. If it's a start ping event, we do this. If it's a response ping event, we do response ping. Respond to ping, right? Otherwise, we cannot handle event of type blah, blah, blah. What's the type, right? That's something that we don't know how to handle. We can only handle these two events, right? And let's see how start ping works. So start ping, takes an event, start ping event, then ping message, ping request, then sequence ID. We create a message, right? This is how we create a message. Then ping message source is c.output as remote. It's my own output, right? Then this event has a destination. This destination is where I need to send it to. So event has a destination. That's my destination. Now I try to send it out. Right? I try to send it out. Assuming it's successful, I record my start time is this time. Right? Then next sequence ID plus plus. So this is a logic of a regular component. Right? We'll see more example later. As long as you don't feel this is totally no way to understand, this is good. No need to remember it. Okay. Notify receive. This is a component notify receive. Whenever we notify receive, we also retrieve incoming. Right? We retrieve incoming. According to a message type, either a request or response, we process them differently. Okay, we process So I typically have this naming convention. This is really Akita's naming convention. We say process message, handle event. Okay. Still convention. There's no certain reason why. If you say process an event, handle a message, it's totally okay. But just to prevent confusion, we try to say process message, handle event. Now notify receive. Now how we handle process ping? Then basically we create an event. We know current time plus 2, right? We say 2-second latency. We just schedule this event to happen 2 seconds later. Then everything we put it in the event handling process. Then handle this message, right? Here we're talking about this process. Respond ping, respond to the ping. Similarly, we create a message. We need to say, oh, we're responding to the original message sequence ID. Then we set a source and destination. Then we output port. We send it through this output port. So there's only one port. So by the way, in Akita, the port is always bidirectional, right? You can send through a port and you can receive from a port. If you want a unidirectional port, you just don't send through it. If it's a read-only port, you just don't send through it. If it's a write-only port, you just don't take message from it. Okay. So all logic is in the component. Okay, so this is simple, right? So when this event happens, create a message and send it out. Eventually, this is handle notify receive again. Whenever we receive this response, we receive it, we get the current time, we can find the corresponding start time, right? We find the corresponding start time, then we simply ping the sequence ID with the duration. What's the duration? What's the latency? Okay, super simple, small example that explains you how this very simple event-driven simulation works. Okay, this is not a full code, although I try to show you most of code is probably less than 100 lines. There's still some boilerplate code to say how to create these components, how the connections are connected. Their code are in Akita repository. You can check it. So wait a minute, then there's a problem here. Do you see any problem? I can tell you the problem is in this line. No, it's not should be locked because the handle will lock everything. Right? Defer means execute this before it returns. Right? So it doesn't need to be locked. What's the problem here? Do you remember what this function returns? Send function returns an arrow, right? Wrong direction. This is send. Send returns a send arrow. So in this example, we're ignoring it. This is a small example. It's okay. It's very unlikely to have network congestion. But what if in a more complex example, in a more complex code, I sent, but I failed because the buffer is being occupied. I don't have enough buffer. So if I want to support that, I will return a send arrow. Whenever there's an arrow, if I send failed, what I can do? Panic? No, panic is not good. So yeah, panic is not good because I still need to continue, right? It's so common that I try to send something, but I cannot. It's very common. I shouldn't panic. It's not something I cannot resolve. We should actually create another event, another start ping event in the next cycle and try again. Right? So then the problem is when we can know we can send out. Just keep retry every cycle until we can send out. Maybe that's 10,000 cycle out. So the notify available method can help, right? The notify available method can help. But just think, I don't want you think about the solution, but at least think about how complex that can be, right? You need to consider this thing for every component, and you retry or you don't retry, you wait notify available. When notify available, you retry. That's super complex, right? I don't want to implement this on my own. So I can tell you, MGPU sim at the early age is a pure event-driven simulation. Very quickly, I cannot suffer from it. I cannot tolerate a pure event-driven simulation. I just think, I really hope I wrote a cycle-based simulation. So but I know event-driven simulation has the advantage of its performance is higher. So I don't want to give up event-driven simulation. That's why I come up with a technique called smart ticking. But before that, I say, what's the problem with pure event-driven simulation? So create events, create a lot of extra code. It's annoying. You need to think all the type of event that can happen, right? Then event can have interactions. Now, what if you have two different events that should happen at the same cycle? Then they're changing different things of a component at the same time. It's really hard to reason about, right? And when you need to retry, very likely you are just doing, for many researchers, computer architecture researchers, their time, they don't want to waste time. They want to do whatever the simplest they want to do. They simply don't want to use the notify available. They just, let's go with retry. Keep retry until it works. Reschedule. If you reschedule an event, it's even slower than cycle-based simulation, right? Because you have to create this event and schedule it, putting in the heap. It's not free. It takes some time. So in this case, we try to use some better method to mitigate this problem, and it's called smart ticking. So we call this event-driven performance with cycle level difficulty or complexity. So in cycle-based simulation, we try to do tick, 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 tick for all the cycles, right? Now it's super simple, but we say it can have slow performance. Then how we can somehow implement a cycle-based simulation on top of the event-driven simulation engine? It's basically this. We do, whenever I handle an event, we let the ticker is the actual component, right? We simply let it tick. So in this case, my component only need to implement the one tick function. Right? I only need to implement one tick function. When I'm done with tick, I just simply tick later. Tick later is implemented in this way. I can find the next tick according to my frequency. I make the tick event at the time. Then I don't care about secondary at the moment. Let's say schedule tick, event.schedule tick. Now just schedule next tick, so it will keep going on. Never stops. So if you write this code, your simulation will never stop. You need some external stopping mechanism. For example, if you're running a program, you need to know like all the instructions are executed. Then you explicitly os.exit at some point, right? So don't expect your simulator engine can stop. You will never, because you always have tick event. Okay, so what about the advantage of event-driven simulation is skipping some ticks, right? So when we can skip some ticks, how we can support skipping ticks? Then, okay, I need to. So let's talk about frequency later. We say if we want to skip ticks, that means those ticks are not necessary, right? Those ticks, if we still tick it, it's not useful at all. So what are not useful ticks? One tick is not necessary. We say whenever the global state will be the same if you tick and not tick, it's the same. In this case, we can safely say this tick is not necessary and we can skip this tick, right? So that means this tick, remember this tick is only applies to one component. So since it will only update the state of this component itself, that means if there's no state update, if it doesn't update any internal state, any register state, we say it's safe to skip this tick, right? Or in other way, if we're not making forward progress is basically a sign of a forward progress means an internal state update or send some message out, successfully sending some message out. If we do not have progress, this tick is not necessary, right? Can you accept this statement? Then, in what case a tick has no update? Two cases, as we said before, right? If this component is fully idle, no request going through this cache, in this case, we say we don't need to tick this element. On the other side, if all the outgoing buffer are full, but we still want to try to send something out, then unless the external environment is changed, this tick, continued ticking will not make any new progress, will not make state change, because we still want to send them out. If we cannot send them out, we have no way to make forward progress. In this case, the tick is not necessary. Okay, so can we test these two cases? Then definitely you can test, say, outgoing buffer if they're full or if they're idle, but it's actually very easy. If we have no progress in one cycle, if we tick a component, this tick function, this component can tell the engine if a progress is made or not, right? It's very easy to detect as it's trying to make a state update. But for some reason, if it cannot, then we say there's no progress in this cycle. So if we have no progress in this cycle, now we have to wait until either this case or this case are being resolved. Then we can continue ticking. Right? So these two cases are when external environment changes, that means for idle, if there's a new task arrives, tasks are from components, right? From another component. So if new task arrives, that means a new message arrives at this component, there may be a new task. Then I need to wake up and continue working on things. On the other side, if one ports outgoing buffer from full to not full state, right? If it's full to at least one buffer slot state. Remember, see how we port implements this thing. Then this is congested. If it's congested, then when this outgoing buffer becomes from full to not full state, then we can schedule this. Then we can wake up this component and start the tick again. Okay? So in this case, we can rewrite a ticking component handle function in this simple way. There are only 2.5 more lines in this code. The made progress part is new. So this tick function needs to tell me if progress is made or not. Is there a state update? And is there you send a message out? Did you send some message out? Then, if made progress, I tick later. Otherwise, I don't tick it. If I don't schedule a new tick event, that means I put this component to sleep. Okay, then we're running out of time and we're also running out of slides. So let's stop here. Let's start to talk about smart ticking in next Tuesday's class.